Hey folks, we're back with another video covering topics in the SOA's Statistics for Risk Modeling exam. Today's video covers the validation set approach. This is the first of two videos on resampling methods, with the next video covering cross-validation. In many real-world applications, we often don't have access to separate test data. Resampling techniques are methods that involve drawing samples from the training data and refitting the model of interest on different samples within the training data. One of the simplest resampling methods is the validation set approach. Here, we take our full available training data and split it into two distinct parts. The validation set is the part we hide. This makes up around 20 to 30% of the data. The remaining 70 to 80% of the data is used for training. The model fit is assessed by minimizing an error function, such as the mean squared error. But there is a problem. The validation set approach has high variance. Since we split the data randomly, the validation set could be anywhere. Maybe it's on the right, maybe it's on the left, maybe it's right in the middle. In the words of the wise statistician M.C. Hammer, you can't touch this. The validation set approach is easy to understand and implement. It also provides a resource-efficient way to estimate model performance. But it has high variance and can overestimate the test error rate, especially for small data sets. Cross-validation is another resampling method that addresses these issues by sampling multiple times from the training data. We'll cover cross-validation in another video. All right, so math time. Let's roll up our sleeves, sharpen our pencils, and break out a calculator, because we're about to get seriously numerical. Here is a sample data set. We have two features, x1 and x2, and our target, y. Our goal is to calculate the mean squared error for the validation set. First, we need to split this up. We'll take the first three observations as the training set, and use the last observation as the validation set. Since we haven't covered model fitting methods yet, we notice that the equation y equals x1 plus x2 fits the training data perfectly. This never happens in the real world, so we'll take it. Perfect! So we can use this equation to predict the target for the validation set. This gives us a prediction function, y hat equals x1 plus x2. We can use this function to predict the target for the validation set. We plug in 4 and 5 for times 1 and times 2 and get 9. But wait! The actual value is 10. We predicted 9. Oh no! So, we were off by 1. Since there's only 1 point, the mean squared error is the mean of that error squared, which is just 1. Now, let's shake it up. What if we used the first 2 points for training and the last 2 for validation? We'll stick with the same model, y equals x1 plus x2, since it still fits those first 2 points perfectly. Running the numbers quickly, for the first validation point, 3 plus 4 is 7. Oh yes, 0 error. For the second one, 4 plus 5 is 9, but the actual is 10, so error of 1 again. Deja vu. To get the MSE, we average the squared errors. That's 0 squared plus 1 squared divided by 2, giving us 0.5. Relatively speaking, this is a simple calculation for a simple model. We'll see how this example can get more complicated when we discuss cross-validation in the next video. Oh yeah, and I guess we didn't really need a calculator for this one. All right, so let's talk about out-of-sample validation. The validation set approach is discussed in ISLR, whereas the out-of-sample validation is from freeze. The process is nearly identical, with the biggest difference occurring in the assessment step. I'm not really sure where phrase out-of-sample validation comes from. Referencing against other sources, it seems like out-of-sample validation is a more general term for resampling methods. Either way, the nomenclature isn't really that important. We'll explain how it appears in the source material, since that's what's being tested. But if you happen to read the source material, let me know how you interpret it in the comments below. Also, if you like what you see so far, be sure to like and subscribe to the channel. So going into the out-of-sample validation procedure. Step 1. We split the data. We take our total sample size, n, and randomly split it into two pieces. So far, this is the same as the validation set approach. We have the training sample size, n1, and the validation sample size, n2. Similar to the validation set approach, this split is random. Step 2. We fit our candidate model using only the blue training sample, ignoring the red test data completely for now. Step 3. Prediction. We bring in the validation sample. We use our model to generate predictions, the y-hats, for these new data points. And finally, assessment. We measure the distance between the actual red dots and our predicted yellow dots. Square those distances, sum them up, and you get the sum of squared prediction errors. Ideally, we want this number to be as small as possible. Let's discuss the criticisms of both the validation set approach and the out-of-sample validation, of which there are many. Typically, we run the model many times for several random splits of data. This can be time-consuming for larger data sets, since we need to estimate parameters and predict values for each split. Results also depend on the random split, and since it's random, we depend on a bit of luck to find the best split. There's also the issue of determining the optimal split size. While the recommendation is to use most of the data for training, there's no agreed-upon percentage that is best. It depends on the dataset and the model. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.